Hi everyone, hope all of you are doing very well. In this video, we'll continue our discussion of preparation of alcohols. And in last video, we learned about the preparation of alcohols from alkenes. And the reaction that we studied was the acid catalyzed hydration of alcohols to form acid catalyzed hydration of alkenes to form alcohols. And in this video we'll discuss yet another important reaction of preparation of alcohols from alkenes by hydroboration oxidation reaction. It's very important reaction, and its mechanism is going to be a little bit complex, so we have to very attentively try to understand the reaction and its mechanism. This reaction was first reported by Herbert Charles Brown in 1959, and the reaction is actually the alkene reaction with diborane. Alkenes react with diborane to give trialkyl boranes. In the first step of the reaction, we get trialkyl boranes as addition product, and this addition product, that is trialkyl boranes, then undergo oxidation reaction with hydrogen peroxide, okay, in the presence of aqueous sodium hydroxide, and in this reaction we get alcohols. This reaction is very important as far as the yield of the alcohol is concerned. That's in this reaction we get a good yield of alcohols. A good yield is obtained in this reaction. Okay, we'll try to understand all the aspects of this reaction, and we'll also learn the mechanism of the reaction. So first of all, we should know about the diborane. Diborane is actually a boron hydride. It's a boron hydride, and this is the dimer of boron hydride. Okay, BH3. This is boron hydride, and when two molecules of boron hydride combine, they form the diborane. Okay, we can also write diborane as 2B2H6. So in this reaction we are using this diborane to first yield the trialkyl boranes. Okay, that is three alkyl groups are attached to boron atom, and this compound, this hydroboration product, then undergoes oxidation and we get our desired alcohol. Okay, so this is a general reaction. Here we have taken the example of propene. Propene is reacted with BH3. Okay, BH3 is borane, and this is the monomer of boron hydride, and in this reaction actually the borane is used for the formation of alcohol. Okay, we add in solution, we add diborane, that breaks into its monomer, and the monomer is then used for the reaction. And we also use this THF, that is tetrahydrofuran, tetrahydrofuran, okay, furan, furan. So this is used as solution, and the work of this THF, tetrahydrofuran, is that it stabilizes this boron hydride. Okay, why? Because this boron BH3, boron hydride, that is borane, also called as borane, this is very reactive, and it never stabilizes until it reacts with another boron hydride to form the dimer. But in our reaction we need only borane, and to stabilize this boron hydride, we are using this THF, tetrahydrofuran. Okay, this just stabilizes. The work of this THF is to stabilize the BH3 and prevent it from reaction with another BH3 molecule to form a dimer. So this is the work of this THF, tetrahydrofuran. And if you know the reaction of the structure of THF is something like this. This is the structure of THF. This is just an ether, okay, ROR group. So in the first step, we react the propene with BH3 in the presence of THF as solvent, and in this step we get tripropyl borane. In this case, in this example, we are getting tripropyl borane, and generally we can say trialkyl boranes we get. Okay, this on oxidation with H2O2 in the presence of a base, that is we're using in this case sodium hydroxide is most commonly used, which bears as the hydroxyl ions, and this acts as base, and in this reaction we are getting the propanol. Okay, we are getting the 3 molecules of propanol. As we already said, we are getting a good yield of alcohol in this reaction. Okay, before discussing the reaction mechanism, we should remember some key important uh, points that are related to this reaction. First of all, the overall transformation is from alkene to alcohol. Okay, the water is added across this double bond. One of the carbons gets the hydrogen, and the other carbon is bonded with hydroxide. Okay, so there is the addition of water across the double bond in this reaction. The reagents in the first step of the reaction, the reagent is boron hydride with tetrahydrofuran as solvent, as we have already discussed its function. And in the second step, that is the oxidation, we have hydrogen peroxide and sodium hydroxide. Okay, here you see I have just given a color code. The hydrogen atom which is attached to the alkene, that comes from the boron hydride, and the hydroxide ion that's attached to the alkene comes from the hydrogen peroxide and sodium hydroxide. This part of the reagent. Okay, this we have to remember because it will help us to solve the problems from this reaction. Okay, it will make easy for us to solve many problems, so we have to remember this directly. Okay, then next the important point is that the product that we get in this reaction, that follows the anti-Markovnikov's rule. Okay, that is the most substituted carbon gets hydrogen, and the least substituted carbon gets the hydroxide ion. Okay, why this happens, we will discuss it in the reaction mechanism, and this is the regioselectivity in the reaction. And if we talk of stereochemistry, so the reaction is stereoselective. The addition is syn, that is the hydroxide ion and the hydrogen, they attach on the same side of the alkene. Okay, if this is alkene, on the same side of this alkene, the hydrogen and the hydroxide ion are attached. Okay, nothing happens like this, that the hydrogen is in one plane and the hydroxide ion is in another plane. This doesn't happen. Rather, the addition is syn. Why this happens, this will be also discussed at the time when we discuss the reaction mechanism in detail. So if we look at the mechanism of the reaction takes place in 2 steps. As I already said, the first step is hydroboration. The first step of the reaction is hydroboration, and the second step is going to be oxidation. In hydroboration reaction, what happens, we'll try to illustrate this by simple example here. But before discussing that, we'll know a little bit about this boron hydride. Okay, if we talk about boron hydride, boron is attached to 3 hydrogen atoms. First of all, this boron is a violation. This bonding of boron hydride is violation of octet rule. In according to octet rule, a compound, a molecule, a metal ion, that when it combines to the to other atoms, it tries to complete its octet. Okay, and it becomes stable only when its octet is complete. But in case of boron hydride, it's happy only with these 6 electrons. Okay, this 1 2 3 4 5 and 6 electrons it's having in its in its valence shell, okay, of this bonding, molecular bonding orbitals. So it's happy with these 6 electrons only. If any fourth bond comes, it becomes very unstable. Okay, so in boron trihydride, there is the violation of octet rule. Okay, and also the boron has one empty p orbital. Due to this empty p orbital, it is susceptible to attack from other other atoms. Okay, it's susceptible to reaction. Other entities, other guys come and they want to attack it and take this empty p orbital. But the boron always tries to be to have only this sextet. Okay. Another thing that we have to remember here is that the boron here is because it is a metal hydride, the boron is having a del positive, a small positive charge, and all other hydrides are having the del negative, small negative charge on them. Okay, so this makes this boron atom, this boron hydride, a very electron deficient. It's very electron deficient, and hence reactive. Okay, hence it's reactive. One more point we have to remember here is that since in the solution, when we are taking this undergoing this reaction, in the solution we have another BH3 molecules. In the first instance, as we first told, that we have this dimer of boron hydride, we have diborane. This diborane is first converted into its monomer, boron hydride, borane. Okay, this is diborane and this is borane, because we need this borane in the reaction. Okay, but it always tries to dimerize. And as I already told you, that in this reaction we are using THF as solvent. The function of this THF is to prevent the dimerization of this BH3. Okay, and we want this reactive BH3 in the reaction, because we are actually undergoing the transformation of an alkene to alcohol. So we need this boron trihydride, we need this boron hydride in the reaction. So to prevent the dimerization, we are using tetrahydrofuran. Okay, nucleophile, and this boron hydride is in this case is the electrophile. Okay, this is nucleophile, this is electrophile. When they interact, what is going to happen? A small positive charge will also arise on this carbon, because these pi electrons are going to shift, okay, towards this boron, and a little del negative, a small negative charge is going to develop on this carbon. Okay. Now there is interaction between this negative charge. Why the positive is here and negative is here? Because this positive, although the carbocation is not formed in real sense, just to view it, we say that we should look at it like a carbocation, although no carbocation is formed. Okay, a del positive charge is developed and a small negative charge is developed here. So positive will be here because it is more substituted, and we know that the more substituted carbon will be, the positive charge on most substituted carbon will be more stabilized as compared to the less substituted carbon. So something like this charge develops in these two entities, and in next step what's going to happen? We get a transition state. Like this. Okay, this bond is going to break. This bond is with hydrogen. This carbon will make the hydrogen bond with this. This will make the bond with this hydrogen, and this carbon is going to make the bond with boron, and also this bond is going to break. Rest will be as it is. Okay, and this is the transition state. And you know the transition state is a very short-lived species. Transition state is a very short-lived state. Okay, the species cannot be isolated. It's formed within 10 raised power minus 6 seconds almost, and after that the required product is formed. And in this we are going to get hydrogen attached to this carbon, and we have BH2 now here. Okay, so one hydrogen has been substituted to this position. Okay, or we can say that one of the hydrogens of this boron that has been substituted by the alkyl group, okay. Here we should understand 2 points. We have to understand here that why the reaction is Markov anti-Markovin curves, and why this is the syn addition. Okay, the reaction is anti-Markovin curves rule because follows this rule, because as you look at this the charge on these entities here, the negative charge is going to interact with positive charge in this carbon, and the positive charge on this boron atom is going to interact with the negative charge of this carbon. Okay, because the boron is less electronegative than hydrogen. Hydrogen is more electronegative than boron. That's why there is a del positive charge on boron atom, and it's going to interact with an opposite charge on this carbon. That is why the addition is anti-Markovin cause rule. The boron hydride is attached to the carbon which is less substituted, not the more one. This is more substituted, this is less substituted, and boron interacts with this carbon. Second thing, why the addition is syn. In this case, you look, the addition is syn. This is a syn addition. Why addition is syn? Because this step, the first step, that is the hydroboration reaction of this mechanism, it's a concerted step. Okay, that is the making of CH bond and making of CB bond. These two bonds develop simultaneously. Everything here goes simultaneously, not the individual steps that the hydrogen is first removed and then it's attached to this and then boron. Nothing like that happens, but all things go in a single step, and it's a concerted mechanism. So that's why the addition is syn. That is, the addition is syn means that the hydrogen and this boron, they attack on the same side of the double bond. Okay, so this is the first step of hydroboration, and this step is going to repeat more 2 times. Okay, again 2 times the reaction will repeat, and these 2 hydrogens will also be removed and they will be substituted by our alkyl group, as in this case. And what we're going to get in that case is a boron that is attached to 3 alkyl groups. Okay, boron now is attached because in 2 successive steps these 2 hydrogens are kicked off, and in that place we are getting in the same way we are getting the 2 alkyl groups attached to and in to this boron. Okay, and in the net reaction we are getting a boron that's attached with 3 alkyl groups. That's why we call it as tri-alkyl borane. So this is the first addition product of hydroboration. Okay, now in next step, this trialkyl borane is going to undergo oxidation and will get our required alcohol in this reaction. Okay, oxidation. Now let's try to look at the oxidation step. In oxidation step, we are using hydrogen peroxide. We are using hydrogen peroxide, that is H2O2, with sodium hydroxide. Okay, with sodium hydroxide. So H2O2, if we open this structure, the structure is like this. Okay, it's like this. and when we add sodium hydroxide in the solution, we are getting sodium ions and we are getting hydroxyl ions. Now a simple acid base reaction is going to occur in this reaction. Okay, this reaction is simple acid base reaction is going to occur. This won't act anymore, and the hydroxyl group will just take the hydrogen, one of the hydrogen atoms from the peroxide group, and hydrogen, the oxygen will get electrons, and we get, in this case we get HOO negative. Okay, this is the unstable anion we are getting. This anion is unstable, and unstable means that it's going to attack any entity that is electron deficient. Here this is now a nucleophile. Okay, it's having more negative charge, and it loves the nucleus, loves the positive charge. That's why it's going to attack any positive charge, any electrophile that comes in its way. In the hydroboration step, we got trialkyl borane like this. So these are three alkyl groups. For convenience, so that our mechanism will be easy to write, we will just show trialkyl boron as, sorry, these are R groups. So we'll show in this oxidation step, we'll just represent these alkyl groups with R. Okay, just for our convenience. Okay, convenience of representation, we'll be writing it like this, Br3. Okay, so what happens in oxidation step? As I told, the first thing here is the deprotonation of this peroxide. Since this oxidation is a multi-step process, this is a multi-step reaction. So in the first instance, the hydroxide ion takes this hydrogen, that is the deprotonation takes place. Deprotonation of peroxide ion gives us this anion, which is very unstable and hence very reactive. Now this anion is going to attack on the trialkyl bromine. Let me represent the trialkyl sorry, not bromine, I am repeatedly saying it. It is trialkyl boron. So these are three R groups attached to it. Now we have this peroxide, sorry, this is anion, this unstable anion, which is very reactive. This now acts as a nucleophile and will be attacking on the boron. Its attack on boron will be like this, and we'll get a structure. The product of this step will be like this, and boron is now attached to, in this step the boron will be attached to O, and this is the anion. This anion will be attached to this boron in this pattern. Okay, we will just show the lone pairs also. It is good to represent lone pairs of oxygen. Now in next step, what's going to happen? This step is a little bit where students get difficulty to understand. Here the pair of electrons in this bromine and carbon of this alkyl group, they migrate to oxygen. This pair of electrons, they migrate to oxygen. Okay, they migrate to oxygen, leading the breakage of this bond. Now see, in this product here, in this product here, the boron is having 4 bonds. So it's very unstable with these 4 bonds. It will just kick off. The only option with the boron is to kick off this CBC bond, to break this CB bond, instead of, because this bond is strong as compared to this. So the only option with boron is to break this bond. So what happens here is this CB bond, that C of this alkyl group and this boron, this breaks, and this electron pair is shifted to oxygen. Okay, and consequently what's going to happen, this oxygen oxygen bond is also going to break. This breaks, leading to the formation of a bond between boron, and we have now these two alkyl groups, and now we have this boron, oxygen, and now this R group that was present at this position, it has now been shifted to this oxygen. So we have this OC bond formation, and we also be getting in this step hydroxyl ions. Okay, we have to just give a little attention to this step because it's a little bit difficult to understand. It's just a kind of shift, 1,2 hydride shift, as we have seen in acid base catalyzed reactions or alkyl shifts. But except what happens here, that instead of migrating to empty p orbital of a carbocation, as we have seen in that case, the electron here, the electron in this case, the electron pair in this case is essentially performing a backside attack on the sigma star orbital of weak OO bond. Okay, so for the understanding of this, we should be very clear about the molecular orbital theory. So that's not a discussion this time. So what simply we have to remember that here is a shift of this electron pair to oxygen, and we are getting a new bond between oxygen and carbon of this alkyl group, and a hydroxyl ion is furnished in this step. Okay, next what's going to happen in next step, this reaction is going to again repeat two times with two more anions of these reactive anions. The reaction is going to repeat two times. Okay, and on repetition of the reaction, we'll be getting boron attached to three OR groups, and now we have in the reaction we have a lot of hydroxyl ions. Okay, we have a lot of hydroxyl ions. Now what's going to happen again, this OH now is in reaction, and it's very reactive also. Now it's again going to react, attack on the boron, because cetyl boron is having empty p orbitals. If you look at this, it's having three bonds, and it has cetyl empty p orbital. So cetyl, it's very reactive, and OH negative being very reactive, it's basic and hence very reactive. It will try to again attack on the boron atom. Okay, so it will do so, and it will attack on this boron atom. So we will look at this, what is happening, we'll be looking at. So up now we got a boron atom that is attached to three alkoxide groups. We call OR group is called as alkoxide groups. Okay, now, and we have very reactive hydroxyl ions, a lot of hydroxyl ions present in our reaction system. So again, as I told, that this is having an empty p orbital and is very susceptible to attack from this hydroxide ion. So the hydroxyl ion is going to attack the boron, and the only option remained with this boron is to kick off the OR group. Okay, the lone pair of electrons will be given back to oxygen, and will be getting a boron that's attached to alkoxide group, another alkoxide group, and now one OH group. And in this reaction, and in this reaction system, we'll be also having now OR groups, this alkoxide groups. Okay, and the same step will repeat two times or more. Okay, and finally we'll be getting a boron that is attached to three hydroxyl groups, and in the system we are getting OR negative. Okay, that is alkoxide groups, we'll be getting 3 alkoxide groups, as in this case we'll be getting 3 alkoxide groups. Now this alkoxide group is again very reactive. It will react, this will react, and the entity which is present for its reaction is the water. The water present in the solution. What's going to happen, this will attack this hydrogen, this oxygen will attack on, this will take one of the hydrogens the from the water, giving the lone pairs to oxygen, and the yield here is ROH. Okay, we'll be getting ROH, that is the alcohol. And if we substitute the R group that we have taken in our initial example, we have propene. Okay, this is the R group, this is the R group that's attached to alcohol, and we'll be getting 3 alcohols in this reaction. So this will be our final product that we get. And in the solution, reaction solution, again we'll be having lot of hydroxyl groups, as the hydroxyl, this only acts as a catalyst in this reaction. We'll again get this, and the alcohol will be our will be the required product that we have got in the reaction. Okay, so here is the completion of the oxidation step. So what we learned is that in the first step of the reaction was hydroboration, in which we have got alkyl borane, and the trialkyl borane was oxidized by hydrogen peroxide. And in the reaction of which is, let's do some simple examples based on hydroboration oxidation reaction. Here we have taken a simple alkene, and we have 4 different conditions, 4 different reagents in this reaction. Okay, in first instance we are going to react this alkene with, we have diborane, and we have diborane with tetrahydrofuran, and we have hydrogen peroxide and hydroxyl ions. So what will be the product? As I already told you that the product of the addition, hydroboration, oxidation is that follows the anti-Markovnikov's rule. Okay, and the product is syn if we talk about the stereochemistry of the product. And third important point that I have already told is that we have to recognize the 2 species. Okay, that is the see, if you look at the hydroboration oxidation reaction, as we have already discussed, it's the addition of water across this double bond. Okay, at one of the carbons where the hydrogen is attached, and at another carbon the hydroxyl ion is attached. So we say that it's the addition of water, or we can say hydration across the double bond of an alkene. So the product, as we have already said, is anti-Markovnikov's rule, and is according to the stereochemistry is syn. But one point that we have to remember is the hydrogen that is attached to one of the carbons comes from the diborane, that comes from the diborane or boron hydride that actually we use in the reaction BH3. Okay, the hydrogen comes from this, and the hydroxyl ion comes from the second reagent, the reagent of the second step of the reaction, oxidation step. Okay, so this reagent furnishes the hydroxyl ion, OH negative ion, and this reagent furnishes the hydrogen ion. Okay, now it will be very easy for us. So what will be the product? To determine the product of this reaction, we do not need to go into the detail of the mechanism, as if we have already understood the mechanism, then we can directly predict the product of the reaction. Okay, so as we know, this carbon is more substituted, so the hydrogen will be attached to this carbon, and hydroxyl ion will be attached to this carbon. Okay, this is simple. Now looking at this example, again we have same alkene. Again we have same alkene. Will again be having syn addition, that's hydrogen and hydroxyl ions will be syn. Okay, now in this case we have to be clear that in this case we are using the deuterium, we are not using the hydrogen. Okay, so the product will be OD. If we know this thing, where from H comes and where from hydroxyl ion comes, then we can directly predict the product of the reaction. Okay, so it won't be it will be OD in this case. Okay, and again we can similarly predict the product of this reaction. Again H will be here, and sorry, because we are again using in boron hydride, we are not using hydrogen, we are using its isotope, that is deuterium. So in place of hydrogen it will be deuterium. Okay, this you can only write if you know the H comes from this reagent. Okay, and OH comes from this reagent, and you will attach the OH at this carbon simply. You don't need to go into the mechanism in this part. In this is the third part of the question, and this is the fourth. Okay, so again we'll be attaching, we know this BD3, and it will be deuterium here, and the here it we have again the isotope of hydrogen here, so it will be OD. Okay, this type of questions may be asked in our exams. Okay, let's look at another simple example. Let's have an example. Take an example of cyclic alkene. Okay, if this is an alkene and we are given with the reagents, we have B2H6 with THF, and also we'll be having H2O2 and hydroxide ions. Okay, normal reagents in this reaction we have. So what we'll be doing, we'll again check all the points. We'll check the stereochemistry. Again it's anti-Markovnikov's rule, it will follow that rule. We have to do the syn addition, and we have to also look at the source of hydrogen and source of hydroxide ion. Okay, so simply we'll just write the product as it will be hydrogen. In this case both the carbons are same. Okay, there is nothing like more substituted, less substituted, so we can attach the carbon to this the hydrogen to this carbon, or this carbons are we are free to do that. Okay, so hydroxide ion will be attached to, but in this case we have to show the stereochemistry also. Since the addition is syn, so we'll show these bonds by wedge shapes, or we can also show both these bonds by the dashed wedge. Okay, so this wedge shape bond shows that both hydrogen and hydroxyl ion OH, they lie on the same side of the in their both are above the plane. Okay, they are above the plane of this remaining molecule. So this is to be, maybe you are given a question like you have options. Okay, you have to choose, you will be having another option like this. Okay, wedge negative, or you will be having another option like this is hydrogen and this is hydroxyl. So you have to opt from one of them. So you have to check the stereochemistry. See here the stereochemistry, the hydrogen is below the plane, hydroxyl is above the plane. In this case hydrogen is above the plane, hydroxyl is below the plane. Okay, so this is not the product, this is not the product, only this will be the product. Okay, one more thing that we have to check, the chirality. If there is any chirality arises at any carbon, then we can get the multiple products. Okay, but if you check this molecule, none of the carbons, this carbon is not chiral, this carbon is not chiral. Okay, so let's take an example to understand this. If we have again the same, we have again the same alkene, and now we are reacting reagents. We have BD3, okay, BD3, and we have tetrahydrofuran, and we have hydrogen peroxide, and we'll be having OH negative. Now in this case again we'll make the product. The product will be both the deuterium and the hydroxide ion will be above the plane. They will be above the plane. Will be above the plane, in the same plane. If you look carefully in this product, you will see that we have two chiral carbons now. This is a chiral carbon and this is another chiral carbon. To this carbon we have four different groups. This is a different group. We have one hydrogen that's not shown here, and this is a different group, and this is CD. This is also a different group. So this is chiral. Again, this is also chiral because four different groups. We have D here, we have another different group, we have different group. So four different groups are attached to this carbon. This makes this product to be chiral. And the another product will be the mirror image of this. That will be the mirror image of this. Let's show this by dashed lines. Okay, this we have shown by wedge, that will be shown by dashed line. This will be another product of this reaction. Okay, we have two more because the syn addition, by rule there should be four products, but since this addition is syn addition, other two products are not possible. In the other two products, in one case the hydrogen will be above the plane and the D will be below the plane, and in the fourth case the D will be above the plane and hydroxyl ion will be below the plane. But those two products are not possible because this addition is syn. So only two products are possible here. So sometimes we can get the question, predict the number of products that can be produced in this reaction. So we have to look for any chirality. Here we have this molecule is chiral, this is chiral, and this is achiral. Okay, so we have to look for the chirality. If there exists a chirality, then we have two products for hydroboration oxidation reaction. Okay, let's take another example. Again, let's take a cyclic compound, and we have an external alkene attached to this this carbon. Okay, this is an alkene. The double bond is outside the ring. So taking the reagents, we'll be having, again we'll take B2H6, same reagents, and we'll be having in oxidation step we'll be having H2O2 and OH negative. In this case again we have to look for the same product. This will be, no change will be in this part of the compound. So the change will take place here. We'll be having hydrogen at this carbon and hydroxyl ion at this carbon. Okay, let's take another example. Let it be again cyclic, because if you can do it for cyclic, then for acyclic it will be very easy for you. So let the alkene be like this. Okay, and taking the same reagents, we have BH3 for example, and we have THF, we have H2O2, and we have hydroxyl. So we have to predict the product in this case. So what will be the product? The product will be at this carbon. This is it will be hydrogen, and at this carbon we'll be getting show like this, not like this, hydrogen, oxygen. Okay, alcohol. So these are some simple examples, okay, to understand. So what we have to keep in mind in this reaction is that the reaction is anti-Markovnikov's Markov-Nichols reaction, it is syn addition, and the source of hydrogen is BH3. We'll continue our discussion, and in upcoming videos we'll be discussing other methods of preparation of alcohols.